Welcome to the second episode of Zero to Autonomous in FRC Java. Today, we will be writing a robot code that operates multiple robot mechanisms at the same time. Last time, we programmed the teleoperated mode and the autonomous mode for a chassis. In this video, there will be 3 additional mechanisms on the robot: a robot arm, a ball roller intake, and a pneumatic hatch intake. The robot we'll be programming is our team's 2019 robot. For the chassis, on each side there are 3 wheels and 2 sim motors. The 2 motors on each side together power the 3 wheels. The main mechanism is a single jointed arm, which is also powered together by 2 sim motors. At the end of the arm, there is a roller intake for the balls using one 775 motor. There is also a pneumatic hatch intake using a double solenoid. For the solenoid, there is a pneumatic system. For each motor, we've added a kind of sensor called the encoder. Why do we need encoders? Let's look at last time when we wanted the autonomous mode to drive forward for 10 feet. We had the motor spin at 60% speed for 3 seconds. In theory, this works, but we're ignoring some outside disturbances that may affect the accuracy. For example, we didn't account for air resistance, friction in the gears, the robot battery level, and so on. Therefore, by simply outputting a percentage to the motor cannot guarantee it to spin a certain rotations. The solution to this is to add a sensor to monitor how many rotations the motor has spun, and the sensor is called the encoder. In this video, we will be using encoders for the drivetrain and the arm. In the last video, we had spark motor controllers because they are simple. While they could be used here, we will be demonstrating how to use the TalonSRX because they have some powerful features for more advanced topics later on. However, because the Talons are quite expensive, Victor SPXs can sometimes be a substitute. Victors don't have the functionality of Talons, but they can follow the commands of Talons. So if you have 2 motors always performing the exact same movement, we only need one Talon to calculate the output and have the other follow that Talon. In the previous video, the main teleoperated code was in the Teleoperated function. We did 3 things there. First, we read the joystick inputs. Then, we did some calculations on the inputs. Finally, we outputted the results of the calculations to the motors. Here is the animation of how the Teleoperated function interacts with the robot. On the left are the joystick inputs. On the right are the motors to be controlled. In the middle, the code runs line by line, from top to bottom, doing those 3 things that we've just mentioned. And this function runs 50 times every second, constantly updating the motors to match our joystick inputs. Today, for the 3 new mechanisms, we will repeat those same steps. But first, notice that because some of the motors are doing the same thing, we've replaced some of the Talons to Victors and set them to follow the Talons. We've also added an encoder for each Talon motor of the arm and the drivetrain. The roller doesn't need accurate control, so it doesn't need an encoder. And now to the code. For each mechanism, it first reads the corresponding joystick input, then does some processing, and finally controls the motors. So now, each time this function runs, it will update all the mechanisms. Now let's create a robot project using the Time Skeleton Advanced template, just like in the last video. First, let's create the motor objects. And import the Talon library. On each side of the drivetrain, and for the arm, there is a slave motor using Victors, which follows a master motor using Talons. You may need to update the firmware and find the port numbers on the Talons and Victors. I'll link to the documentation in the description below. Finally, we have a single roller motor. For the pneumatic system, we need one compressor object for the whole robot. And for the hatch intake, we have one double solenoid at the robot's pneumatic control modules port 0 and 1. This time, we'll use two joysticks, one for the driver to drive the robot, the other for an operator to control the mechanisms. Now in RobotAnette, which will run once when the robot powers on, we will set up the Talons. If the motors are spinning in the opposite direction you want, the set inverted command can change the motor's forward direction. Then we will set the slave motors to follow the master's outputs. And we also want the slave motor's inverted settings to follow the master's. Now we will set up the encoders. There are many kinds of encoders and many ways to connect them, but we'll demonstrate connecting them through the Talons. First, we will tell the Talons which kind of encoder is connected. For this robot, the drivetrain encoders are CTRE magnetic encoders. The arm encoder is a Greyhoe optical quad encoder. Similar to set inverted for the motors, we can set which direction is positive for the encoders by using the set sensor phase command. Then, we'll reset all the encoder values to 0. Finally, let's not forget to start the compressor when the robot starts. Unfortunately, the mag encoders on the drivetrain count 4,096 ticks per rotation. But it would be easier for us to work in units of feet, so we are going to do some unit conversion. If we know the number of ticks, we need to first convert it into rotations, then multiply the gear ratio, then convert it into inches from the diameter of the wheels, then convert it into feet. If we simplify this, feet equals a constant multiplied by the ticks. We'll store this constant in the final variable, and multiply or divide it when we want to do the conversion. Similarly, we'll do a tick to degrees conversion for the arm encoder, except it has 512 ticks per rotation and many gearbox reductions. Now that we have set up the encoders, we can easily monitor their values on the driver station computer using the shuffleboard. In the code, we will write into the RobotAnette function, which continuously runs no matter which mode the robot is in. The function isn't visible in the code yet, but once we start typing its name and hit enter, it will show up. And here, we can specify the name and the number to send to the shuffleboard. First, let's deploy the code. On the driver station software, choose to use the shuffleboard. Smart Dashboard could work as well, but shuffleboard has more graphics. In the shuffleboard, go to the left panel and drag the values you want to display onto the main screen. Then, we can choose to display the values in different formats. And now if we were to manually move the robot, we will see the encoder values change. I am turning each mechanism in its forward direction. So if these numbers are negative, go ahead and tweak your inverted settings. That is all for the setup. Now let's write the teleoperated drive code. Just like last time, we will use arcade drive. But first, let's read the joystick inputs. Then, instead of calculating the motor outputs ourselves, we will use a library to do the exact same thing. First, let's go to the top and create a new differential drive object called drive. And it wants our left and right motors. Because the slave motors are already set to follow the masters, we only need to control the master motors here. Then, in Teleoperated, we will use drive.arcadeDrive to calculate the speeds and output them to the motors. We will pass in our desired speed and turn into this function. There's one more caveat with joysticks. Because the springs in the joysticks wear out, they sometimes don't return to their neutral position, which has a reading of 0. The robot won't move because this small percentage output to the motors won't even overcome friction. But if you leave the robot like this long enough, the current may be enough to burn the motors. The solution to this is simply to ignore joystick inputs less than 5%. So in the code, we could write, if the absolute value of the joystick is less than 5%, then we'll set it to 0. In fact, this feature is built into the differential drive library. To get the same effect, we could also write in RobotAnette drive.setDeadband 5%. Now let's code the arm. First, let's read in the operator joystick input, and we'll use axis 1 here. Next, let's apply the deadband and slow it down by 50%. Then, we'll output the power to the motors. The arm could move now, but there's one more thing we could do. When we're operating the arm, we don't want to accidentally overspin it and have it break the front or the back of the robot. Because we have encoders now, we can actually set the code to only let the arm move in a certain region. This safety feature can make it impossible for us to make a mistake. Now let's implement this in the code. Back in RobotAnette, we will set up these limits. First, we will assume that the encoder is zeroed when the arm is at the bottom. So to avoid getting a negative angle, we will say the reverse limit is 0. Then, let's say we don't want the arm to surpass 175 degrees. So we'll convert that into ticks and set it as the forward limit. Now let's enable both limits. What this does is, if the encoder value is below 0, then the motor controller will ignore any additional reverse speeds, and if the encoder value is greater than 175 degrees, it will ignore any additional forward speeds. For the roller, we just want two buttons controlling intake ball and outtake ball. We'll first create a variable containing the default 0 power if no buttons are pressed. If button 1 is pressed, then intake. If button 2 is pressed, then outtake. The getRaw button command takes in a button index and returns true or false, indicating if that button is pressed. You can find the index of a button in the 4th tab of the driver station software. Then, we'll set the desired speed to the roller motor. Finally, for the hatch intake, we want the default to be locking the hatch. And let's say if we press button 3, it releases the lock for grabbing and placing. So if button 3 is pressed, set the solenoid to reverse position, otherwise set it to forward position. Now in Autonomous, we will again make a program that crosses the auto line. But this time, we can do it more accurately using encoders. Before autonomous mode starts, let's reset the encoders to 0 again just to be sure. In autonomous periodic, we will monitor the position of the robot. Let's first get the position of the left and right wheels and convert them into feet. Then, the distance the robot has traveled can be the average of the two positions. And while distance is less than 10 feet, 60% speed forwards, otherwise stop the motors. And that's all for autonomous. And there's one more thing we can do with the motors. Motor controllers give us two settings when the motors are not spinning. The first setting is called brake mode. It lets motors resist outside forces using back EMF. So it has the same effect of having more friction. When we're operating the arm, gravity is constantly pulling it downwards, so we want to use this mode to have the arm stay in place. The second setting is called coast mode. It lets motors to be freely rotated by outside forces. We want this mode when the robot is disabled because humans may try to move the arm, so we want the arm to rotate easily. To achieve this, we will set the motors to brake mode when the robot is enabled and to coast mode when it's disabled. And we can do the same for all other motors on the robot as well. To do this in the code, we will create a new function called enable motors that takes in a Boolean value called on. In here, we will set all motors to brake when the Boolean equals true and to coast otherwise. Now in Teleoperated and AutonomousAnette, we will brake the motors. And in DisabledAnette, we will coast the motors. DisabledAnette is not yet visible in the code, but we can again type its name and hit enter. Now the code is done and let's see if it works. Thank you for watching this video of 0 to Autonomous in FRC Java. If you find this video helpful, your friends might too. So please like or subscribe, and tell your friends about it. Again, all this code is available on GitHub, the link is in the description below. And if this code didn't work for you, or if you have any questions, please send me an email. Until next time, happy coding.